This is part 2 of lecture 8. In part 1, we talked about fading and how we can remedy the effects of fading by applying coding. In this part, our focus is on diversity and diversity combining, and as a method to remedy the effect of fading. Basically, to start this discussion, I come to this figure, and this figure is the one that was my favorite in part 1 as well. And what I say is that the problem with fading is these fades happens like regularly, and each time that I go in the fade, I'm in trouble because I make a bunch of errors. And in data communications, my error rates are like 10 to the minus 5, 10 to the minus 6. That's what I want. But these guys, they go to fade so fast that I cannot provide that. And I have to push the average power way up so that when I go to fade, still I'm above. And that's a difficulty. That's which happens, okay? I need like 30 dB more in fading channels. But anyways, I noticed to this point, that's the key, that my problems are when in particular, I mean, if you're in analog communication, when you have like these fades, like if you're listening to like analog FM voice, it's like a cup, like a sound inside the voice. You may like somehow forget it, okay? But in digital communication, in particular, when you're talking about data, people are sensitive to error rate because they have banking data, etc. You cannot make errors. You cannot accept those errors. So you have to remedy that. Now, the most like reasonable way to think about remedy the fading is that now that I know that my problem is in fading, means that I have like these fade hits. So I know, on the other hand, from a study of the channel models, that these fades are like very random. They are statistically random variables. So why not I remedy that by creating two sources of independent random variable? I mean, this is a random variable which randomly hits this value, this like very low value of signal-to-noise ratio. What is this? What is it representing? This is my received signal. Okay, so if my received signal is in one location and I'm looking at variation of the channel, it's a random variable. If I move a little bit, I have another random variable which doesn't go to fade like this. Okay? Now, so the other one is called another branch of diversity. Question is that, I mean, how can I generate these branches of diversity? Let's look at the most simple and easiest one is the so-called space diversity. If I have one antenna and I know that what is causing these fades? Changes into phase of different paths. Is that right? I have a bunch of paths adding together like this. And this summation, sometimes they add up, sometimes they go against one another. When they go against one another, these phases are aligned against one another. And the phase is changing at the rate of what? Do you remember? At the rate of lambda. And lambda for 1 gigahertz was like 30 centimeters. For 2 gigahertz is like 15 centimeters. So if I change like fractions of lambda, like lambda over 4, for example, phase is changing how much? Pi over 2. So if change phase, all these phases, they change pi over 2, they get like, they will be in a different situation. They are no more in fading there. Okay? So if I change the distance a little bit, I'm going to have a different independent fade. Okay? So the easiest thing is that I take two antennas, I put them close to one another, like around lambda or fractions of lambda away from one another, like lambda over 4, for example. So what will happen is that I have two antennas, one of them receiving this signal, and the other one receives this. Although the statistics of this one and this one are the same, but they go inside the fade independent from one another. Then I would say that my received signal has two branches of fading, or it's a diversified signal which has arrived at the receiver. Okay? This is key to the understanding of many, many concepts which people have applied to improve the performance over fading channels. Basically, what you're trying to do is to provide diversity. Means that I have a random signal arriving in one point. I want to receive another random signal which has the same characteristics, but it's independent from this one. In the space I gave you, if you go like in the order of lambda apart, you receive that, for example, in mobile application and for outdoor application. For indoor, they are more correlated. You have to separate them possibly more. Okay, but that's the only source of diversity. No, there are other sources of diversity. What happens if I change the frequency? What happens if I change the frequency? You remember that frequency f, which is the omega times tau, was what? Omega was my frequency, and then when I change my frequency, my phi phase was omega times tau. Do you remember? So the phase of these components in here, I mean, I have a bunch of paths. Okay? Each path has a phase which is a function of frequency and the delay of arrival. If I change my frequency operation, what will happen? This phi, the phase changes. So the combination of these phasors will change. So I have a bunch of phasors. If the combination changes, so the second type of, in fact, approach that I can take in order to provide diversity is to change my frequency. And in which case I call it what? Frequency diversity. Now, but if I'm sending the same data in different frequencies, I mean, I'm losing the bandwidth. It's not bandwidth efficient. Okay? But if I send different data at different frequencies, then it will become bandwidth efficient. And that's the story of OFDM actually. Okay? But for the basic is like I can change the antennas in a space to provide diversity. And diversity means that the fading that I observe is independent from the other one. Or I can change the frequency so far. The third one is I can change the time. I send the packet, I send it again. One time it hits inside the fade, the next time it doesn't. That's what? Time diversity. But still I'm losing resources by sending again or by sending different frequencies. While when I go to a space diversity, I don't lose resources. If I have two antenna or one antenna, still I have the same data rate. Okay? So my space still has that advantage over frequency and time. Unless I play some tricks again. For the time diversity, again, I play some tricks in there. Okay? If I don't play any trick and I'm like straight, I send the same resource 2 times, means that my data rate drops to 1/2. I use 2 frequencies, means that I'm losing my bandwidth 2 times. But I use 2 antennas, that's 2 antennas, 2 receiver antennas, or 2 transmitter antennas. No different. Now, but, so, the remedy of the thing is diversity, to provide the diversity. And the sources for diversity, I have space diversity, I can have frequency diversity, I can have time diversity, and more recently, one of the popular one is space-time diversity. Okay. Now, coding that I told you earlier, coding in a sense is a sort of what? Time diversity. Any type of that coding. Because when you code, you just scramble your signal and you add some redundancy to that. Redundancy in what? In time. Why do you do that? Because you want to remedy for the time that you go to fading. So, if I come to these terminologies, the coding that I was telling you earlier is a sort of time diversity. Okay? And space-time is a combination of time diversity and space diversity. Means multiple antennas. So, but in radio communication, we are interested in these fading stuff, because diversity stuff, because diversity is the only way to fight with what? With fading. And the intuition is the figure that I gave you in here. Now at this stage, I want to just forget about how I can create the diversity. I'm just trying to develop some mathematical structure to get some conclusions, to see that how effective is diversity. So basically, earlier when I was talking about fading, I got this simple example of Rayleigh fading because equations turned out to be very clean. And based on that, I showed you this famous thing that I lose like 35 dB when I'm exposed to Rayleigh fading. And I have the same average signal to noise ratio, for example. Or the same error rate, for example. Now, so basically now that I want to do some mathematical modeling, in the old time, I had like one branch, and the signal in here was like a Rayleigh fading. Okay, so my received signal Zs of t was what? Was something like AI, which was my symbol, times alpha, the Rayleigh fading, square root of Es plus epsilon. This was my received signal. Now I have my received signal. If I have diversity, for example, I have Z1 of t and Z2 of t. They are the same thing, AI times alpha 1, square root of Es plus epsilon. This one is AI times alpha 2, square root of Es plus epsilon. I have two samples. The difference between these two samples is that these are two random variables, two samples of a random variable. So the numbers in here and here are random variables, but they're two samples of a random variable. And they can be correlated, they can be uncorrelated. Okay? Now, for example, if I had like a space diversity, when two antennas are close to one another, they're correlated, alphas are correlated. As the two antennas get far apart, they become independent. Okay? So this is what two order of diversity. So I have two samples of the random variable. And I'm trying to avoid the time that they have very large. And for that, I want to calculate the error rate. But these are my received samples. I have one received sample, two received samples for two order of diversity. There are two random variables. I can post-process this thing. As soon as I received it at the receiver, I can post-process it. What does post-processing mean? Means that, for example, I can take Z1 and Z2 and say that whichever which is stronger, I take that. So this guy was fading like this, and this is Z1, okay? And then Z2 was fading like this. Okay? So anytime that Z1 is greater, I take the Z1. Anytime Z2 is greater, I take Z2. Whenever I'm in fade in this one, of course the other one may not be in fade. The probability of having both of them in fade is, So if I have this rule that whichever which is larger, I pick it up, I'm combining my fading branches. Fading branch and fading branch. I have two fading branch. I'm combining them. In here, my combining approach is called selective fading, or selective combining, sorry. Means that I receive two branches of fading, I select the one which is stronger. I call it selective combining. I can have another approach. I can take Z1 and Z2, just add them up together. If I add them up together and make my decision based on that, it's called linear combiner or equal gain combiner. Okay? And then I can do a third one. A third one is that I estimate the ALF1, I estimate the ALF2. And I weight the Z1 and Z2. So selective combining was Z1 greater or less than Z2. The one which is greater, I just take it. Linear combining, I just add Z1 and Z2. The third one is that I take Z1, I weight it with ALF1. I take Z2, I weight it with ALF2. And I make my decision based on this. I'm weighting them. Okay? In order to weight them, I have to have estimate of ALF1 and estimate of ALF2 to multiply it with them. This thing is called maximal ratio combining. Maximal ratio combining is like match filtering in fading channels. Do you remember what was the story of match filter? If I receive a signal, I pass it to any filter and sample it, I have a signal to noise ratio. But that signal to noise ratio is maximized if that filter matches the transmitted signal. Here is exactly, this is a discrete match filter. If I have two branches, as if I have an impulse response with two numbers, if I multiply it with the same values, I have matched them. So after sampling, it's optimal. Okay? So maximum ratio combiner is not very difficult to implement, because I receive the signal and I estimate what is the value. Multiply it with the signal. How do you estimate that? You can average it over the bits. And then what I do, I multiply the received signal with that, with this equation, and then I process that for my decision making. This maximal ratio combining, this is selective combining, this is linear combining. Okay? So if I come back to the computer now, for diversity receptions, if I want to have some sort of mathematical infrastructure, and now I have two sets of things in there. I have one set is down here, is diversity techniques. Means that how I can provide diversity, how I can create diversity. How can I do that? I can create it by diversity in a space, diversity in frequency, diversity in time. Okay, or I can combine them. Okay? Now, this is how I can create them. And I discuss them, and that's enough. The second issue, but from now on, I don't talk about like how I created them. I'm just assuming that I have already created, okay, 2 diversified channels or 4 diversified channels. How can I combine them? So I have 1 and 2 channels. How do I combine them? If I select the strongest, is selective combining. If I just add them together and then process that, is equal gain combining. If I multiply this with ALF1, multiply this with ALF2, and then add them together, it's called maximal ratio combining. Maximal ratio combining is like match filter, is the optimum receiver. Okay? This is the basic definitions about any sort of diversity. And these terminologies, now we will get them in more details. But the first step that we want to go, we want to look at like our old story. What was my old story? My fading was Rayleigh. And I want to see quantitatively what is the impact of diversity. In order to do that, we start with this thing. I'm just talking about maximal ratio combiner. This is an example for maximal ratio combiner. So I have a symbol A S of t that I'm transmitting. The channel is only one path, or is narrow band, so it gets multiplied with like amplitude like α0 or α1, which is actually a complex number. This is the magnitude, this is the phase, and this channel and this channel are two different channels because these random numbers are different. These random numbers are representing the channel. Okay, so at the receiver I have the match filters, and then output of the match filter, in one branch I have this, in one branch I have this thing. Okay, this H1 is the channel in here, H0 is the channel in here. Then what I do is that on one hand I use these receive signals to estimate the channel, means to evaluate what was H1 and what was H0. This is called channel estimation. Okay. When I find the estimate of the channel, I then multiply it with the receive signal to form this variable, which is the variable that is used in maximal ratio combining for what? For processing. To see that what was A sub I. After all, A sub I was my digit. If I had binary PSK, for example, this A sub I was equal to what? Plus minus 1. When I receive this decision variable after processing, if it is more than 0, I declare that it was 1 which was transmitted. If it was less than 0, I declare that it was minus 1 which was transmitted. Do you follow me? So this is my story of maximal ratio combiner, an example of how to implement it with two antennas. It's not a very difficult thing to implement. Okay? And modulation technique I assume to be binary PSK. So what is happening in here, in fact, if you want to compare this extra term that you have in here and compare it with what you had with non-fading channels, here now I have these two terms in here. If I didn't have diversity, I had only one of them. Okay? Mathematically speaking. So, mathematically speaking, more or less I'm what I was before. Now, my noise term in here, I have two noise terms, one from this branch and one from the other branch. But at the same time, my signal energy is from one branch and the other branch. Noise is the same, with the same statistic. But when I'm talking about α0 and α1, if one of them goes to fade, the other one may survive. And that's how I have always a decent signal to noise ratio. Not always, much more than before. But these are not quantitative. Now I want to know that what is the impact of this thing. To know the impacts, I have to do something. For example, I have to calculate the error rate or probability of outage. In order to do that, let's come down in here and look at the case in a little bit more mathematical terms. If I have like d order of diversity, so means that I have d branches, okay? Each branch is receiving like the same symbol A sub I, but with a different constant α sub j and a different noise, and the same E sub s. This is what I receive. Okay? Now, if I want to do like maximal ratio combining, I have to multiply each branch with what? With complex conjugate of this magnitude. And alpha j star times alpha j equals to what? Magnitude of alpha j square. And if I add all the branches together, I get this thing. This part. So this is what is coming in here. Now, how about the noise? Noises are multiplied with alpha j's and then they add together, and this is it. So this is my noise, this is my signal. Okay, this is what? This is a maximal ratio combiner. So I have a bunch of like branches. Each branch has its own match filter, and they are sampled. After they got sampled, I have like multiplied them with something, and then I have added them together. Let me just show you that receiver, just to clarify. So I have a bunch of like diversities, Z1, Z2, etc. I mean, diversity 1, diversity 2, and comes to diversity number D. I started from 0 actually. All of them pass through these match filters first. Match filter, match filter, match filter. Okay? And then I sample all of them. When I sample them, in here I have Z1, Z0, in here I have Z1, and this is ZD. Okay? Now, what I do in here is that I will multiply these guys, each of them, with what? This one with alpha 0 star, this one with alpha 1 star, and this one with alpha D star. And then I take output of all of these guys, I add them together. And this is my final, the so-called ZT. Z capital T. This is what I am doing. Okay. Now, what is the equation for Z of T? That's what I have in the computer screen. That's this one. That's this Z of T. The output. This is my Z of T. Now, what I need to do is calculate the signal-to-noise ratio. Signal-to-noise ratio is a square of this over variance of this thing. So, energy per bit, okay, sorry, gamma sub B is ratio of these two, and if you calculate it, it comes up to be like this. So, this is upstairs, you have variance of this guy, and times ES or EB. Maybe I have to change this thing to EB, or change this one to ES, either way. So, for like binary PSK, which is the case that I'm studying in here, they are the same thing, and my gamma sub B at each instant is summation of j equal to 1 to, in here I put 0, so this one should be 0, or this one I put it 1. A lot of yeah, this is 1 actually. Then, so j equal to 1 to d alpha I magnitude square times EB over N0. This is the total signal-to-noise ratio that I have. Okay? Now, how about the average of that? Average of this thing, gamma B average, would be average of this thing, which is the so-called EB over N0. Because summation of these random variables are like, I mean, these are normalized to 1. I normalize them to 1. Now, the point is that what is this? What is the distribution function of this? Earlier, I had alpha j square. What was the distribution function of alpha j square? That was Rayleigh. Sorry, alpha j was Rayleigh. Alpha j square was what? Exponential. Now, this is a bunch of exponential added together. If you get the Fourier transform or Laplace transform and take the inverse, you come to this chi function, which is like this. And these parameters a sub n are given by this. This is the most general form in which alpha j's are correlated. Okay? And these nandas are eigenvalues of the correlation function. Okay. So basically, what we have in here is that if you take the probability distribution function, your signal to noise ratio is this one. Since EB over N0 is a fixed number, so distribution of this guy is the distribution of signal to noise ratio. Okay. What is the distribution of this guy? This is summation of a bunch of exponential. So that would be the distribution function of that. Okay. In which A sub n is given in here. What are these nandas? These are eigenvalues of cross correlation function of these taps. Okay. So you create the cross correlation function like alpha1 and absolute square, and then for next one is alpha1 star alpha2, and then da 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 da. That's a matrix. You find the eigenvalues of that, those eigenvalues of these nandas. Okay. Now, if these are uncorrelated, all of these are, say, this is a diagonal matrix, and all the nandas are going to be equal. Okay. Now, but this one gives you the most general format for the calculation of probability. But anyways, these are only equations for us simple system engineers. Too complex. We want to get to some conclusion somewhere. First, before I go anywhere, let me just tell you this thing, that if you go for probability of outage, you can also show that probability of outage is given by this thing. This one was what? Bit error rate. This is like, if I replace those values inside, A sub n's inside, and this would be my probability of outage. So probability of bit error, similar to the past, is integral over like f of gamma sub b times that f complement function that you have, like a f complement of, for like binary PSK, which is my case, 1/2 f complement square root of gamma sub b d gamma sub b. What is this f of gamma? That's the same gamma function that I had in here, this one. Okay. Now you get this and plug it in to this equation. I'm going to end up to this. And if you plug it in this equation for probability of outage, I end up to this thing. Do you remember, for probability of outage, you get the distribution function of signal to noise ratio, integrate between 0 and gamma sub outage or gamma sub threshold. Sometimes I have called it gamma t, sometimes I have called it gamma out. But, I mean, bad notations. Okay. But anyways, I have two closed forms equations, which are generalized equation for average error rate and probability of it. How did I calculate them? I used the probability distribution function of received signal input to noise ratio in what? I used that in d order of diversities. If I have d diversities. Okay. So first what I did was, this one was 1. First I came up with this distribution function for received signal to noise ratio. Then I took average probability of error for binary PSK over that distribution function. That's what I got. And then I got probability of outage, which is integral between 0 and gamma threshold for that. And I ended up with this. Okay? These are one set of equations. These are the most generalized equation for any sort of like correlation. But if you go to other books, like, for example, John Prokis's book, they have other versions of this. The most popular version is that when they are not correlated, for uncorrelated cases. If branches are uncorrelated, probability of error is something like that. Probability of outage is something like this. Okay? And this is the probability distribution function of gamma sub b. This is probability of outage. This is average probability of error. This is a very good equation, very nice equation. Why? Because you can simplify that to this value. D is the order of diversity. Gamma sub b is your average signal to noise ratio. Okay? And if you remember, now if I put like d equal to 1, this turns for d equal to 1 means that I have one order of diversity, only one branch. This comes up to PB average equals to 1 over 4 gamma B average. Do you remember this? This was probability of error when I have no fading. When I have fading, but I have only one branch receiver. Okay. Now, if you add more orders, this is what it comes in. Now, the question is that if I take now this simple equation, this is the simplest one, which is P B average equals to 1 over 4 gamma B average to the power of D, D order of diversity, times 2D minus 1 D. And this thing is defined in here. Okay, that's a combination of like 2D minus 1 every D, which is defined by this equation. Okay? Now, this equation, I like it. This equation is simple. Up to now, all my equations were a little bit confusing. Too many equations. This equation I like. But I remember that this equation is associated to what? This equation is associated to uncorrelated branches. For uncorrelated branches, D order of diversity, my average bit error rate for binary PSK is given by this equation approximately. And I checked it. For D equal to 1, it's the same as what I had before. Now what I want to know is that I'm doing all of these exercises to get some conclusion, to see how effective is. Okay? So let's just sketch them for different order of these. And these are sketches. Sketches of the same equation. Okay? So this one is actually for binary PSK. PB equals to 1 over 4 gamma B average to the power of D times 2D plus 1 and D. 2D minus 1 or plus 1? Which one was it? Minus 1 and D. This equation, 4. D equal to 1. This is the one that I observed before, and I had this shocking result related to that. The shocking result was that for binary PSK that I had 10 dB signal to noise ratio, I needed 45 dB signal to noise ratio for the error rate of 10 to the minus 5. Now, if I have 2 order of diversity, this is for D equals to 2. Means that rather than 1, I have 2 received antennas. Okay? My requirements come down now to what? Around 25. Already I have saved 20 dB. And if I make it like D equal to 4, means 4 antennas, it comes like 14, which is talking about 30 dB improvement. Isn't that fantastic? So if I have like 4 antennas, I'm very close to non-fading channels. given that the 4 antennas are working on Rayleigh fading, and given that these 4 antennas are uncorrelated. So if I'm thinking in terms of space, I have 4 antennas in the space which are at least order of nando apart from one another. Okay? Now, for different channels, they are different. For like troposcatter ionosphere channels, which you hit the like layers of the Earth and then you come back, they are very much like Rayleigh fading type of channel. So nandos are like, I mean, they put the antennas in order of nando apart. But for the cellular industry, they put it like sometimes like up to 10 nando apart, because we are operating at like 1 to 2 gigahertz. Nando is like 30 centimeters. You can put these things like several meters apart. If like put it 3 meters apart, this is 10 nando. And you're talking on top of like a huge post. It's easy to do. But when you come to the receiver now, however, your receiver is a small thing. How can you provide 2 antennas in there? Now that's a difficulty then. You have to come up with like, one antenna often comes out of the board. If it is like a laptop, you have like about like enough, like 30 centimeters to put 2 antennas in the sides, or 3 antennas in the side. If you have an access point, you can put several of them. Okay? So this is the issue of how to implement them. Implement the diversity and at the transmitter antenna is much easier as from the receiving antenna. But up to now, what we have shown you, you create that independence when you have 2 independent sources. So you want, and often at the base station, at the mobile is the place that you want to improve your performance, because you don't want to waste that much of battery. So you want to have minimum power and have good performance at the mobile. But at the base station, you're plugged to the power and you can increase your power, always full power. And also you have plenty of space for diversity reception. Do you follow me? So the challenge becomes in the design of the terminal. Okay, and the diversity, like a space diversity that I was talking about so far, was a space diversity which was caused by what? By 2 separate antennas, for example. And if I want to have them like even nando apart, I cannot do that. So what should I do in my terminal? What they do often, they have one antenna that everybody sees outside. They can put another one like a rim around the circuit board. And that's two antennas. They are correlated, but better than none. But for the base station, yeah. Now, a space-time coding that I will talk about later is somehow allowing you to provide that diversity at the receiver. Okay, but we will talk about it later on. But up to now, I'm just bringing to your attention that if you have independent, for the Rayleigh fading channel, if you have independent fading, you have like 4 antennas, that 30 dB that you were losing, 35 dB, you gain a lot of that back. You lost 35 dB because of fading, you get like 30 dB back with 4 antennas. So as drastic is the effect of fading, diversity fights that very effectively. Okay, but practically now, how can I create these diversities using different technologies? That's the story that we will have rest of this lecture and the lectures which comes for wideband. Okay, always we are thinking about how to create diversity. Okay, but at this stage, the simplest was a space diversity, and for the space diversity, we noticed that creating a space diversity at the receiver, when the receiver is base station, is easy, but for the mobile, it's challenging. Okay. Now, With that, we have more, in fact, equations that I have left in here. For example, if you don't have even branches or you have selection diversity, you have these equations for calculation of error rate. Now, how do you derive these things? We are not that interested. But if you want the detail, you go to book by John Prokis, and some of them they are coming from the literature, papers. But what we are interested is just knowing that whether there is a closed form. These equations are closed form equations, which are easy for getting conclusions. Okay, so we have closed form equations for uneven branches, for selection diversity, for maximum ratio combining, all of them for Rayleigh fading. And more are available also in the literature for Nakagami, for the Ricean, but you have to search the literature. But most of the realistic channels are multipath channels. For them, we don't have any closed form at all. So we have to do simulation and find the performances. These closed form equations, they're giving us the intuition. I mean, if I didn't have these equations that I had to introduce you today and the few curves, you wouldn't appreciate how important is diversity and how bad is fading. So we use the equations to develop that intuitive understanding of what will happen. Now, if you want to compare it with non-fading channels, people who are designing modems, baseband, voiceband modems, they're always fighting for 3 dB. Because with each 3 dB in QAM, you can add 1 bit. So if you have 2400 bits per second, 1 bit added, it goes 4800. 1 bit added goes 7200. So that has been always a challenge for voiceband modem guys, to take the probability of error versus signal-to-noise ratio and try to improve that 3 dB with a trick. What were the tricks that they discovered? The most popular one was QAM modulation that we had a little bit earlier. And then they find trellis code modulation, which was very, very effective. Other than that, telephone company was improving the signal-to-noise ratio of the lines. And that's how they could go to from early voiceband modems, which were 300 bits per second, to latest ones, which were 36 kilobit per second. Then they had 56 kilobit per second. How did they do that? 56 kilobit per second. They have completely changed the line. They're new lines. They're not old lines anymore. So they don't have adapters in there. So the story of voiceband modems have always been that using and regular codings are not effective for voiceband modems. In non-fading channels, they are not. So it comes to going to more complex modulation techniques. Now, when you come to fading channels, the issue comes to be how to create diversity. Okay, and people are not interested in 3 dB as much. They are still, for different reasons, for saving the battery time, etc. But with the diversity, I'm gaining things like 10 dB, 20 dB, 30 dB. Those are things that are foundation and basic difference between voiceband modems and radio modem technologies. Okay? And in terms of channel, voiceband modems are the so-called slow time varying channels, but they are not fading channels. Radio channels are fading if they are narrowband. If you go to wideband radio channels, they are frequency selective fading. the difference between frequency selective and flat fading is that in flat fading, your pulse shape doesn't change. In frequency selective, your pulse shape changes. Okay? And those are the topics that we will study later. But coming back to where we were so far, what I did was I told you that in order to see the effect of radio channel fading on the performance of the modems, I picked up this Rayleigh fading channels, and then I showed you how bad it is. And then I told you to get out of that, you need to provide diversity. And in between, I had one example, which was coding, which was a source of, we referred to that as time diversity. Okay? And then on top of that, I said that there are some closed form equations. I gave you a bunch of closed form equations to relate the error rate to average signal to noise ratio. The last topic that we want to cover in this lecture 8 is space-time coding and the MIMO, which I will have just a very brief and short overview of that. Before we go there, why not we take another break